Is it good? Hello, everyone. Yeah, sorry to keep you waiting. We were setting everything up, but we're ready to start. I just want to say thank you, everyone, for being here. There's a lot of people. We're really excited to have you here. It's been almost like what, 1.5 years since we've been able to meet up as a club. So yeah, like I said, we're really excited to show you all of the progress that we have done during the pandemic and even prior to the pandemic. So before we start the slide deck, I just wanted to introduce our PhD advisor, Adam Zufall. Just as a quick bit of background, Adam works under Professor Robinson at the HR VIP lab. He has worked at NASA Ames Research Center for 4 years, where he focused on attitude determination and control systems. Oh man, sorry. And lastly, Adam has been with the club for a while. He was the club president back in 2016. So it's great to have him back. And yeah, with that said, Adam, if you'd like to share a few words. Oh, right here.
Thank you, Chris. And with that introduction, that took like the first 60 seconds of content I wanted to share. But again, I'm really happy to be back. It's been a while, but I'm really excited to bring what I've learned working at Ames, share with you guys, share with the club. And talking to Melina earlier, I realized the most important things to share with you guys is not so much what I've done, because, you know, satellites are cool and all that, but you'll learn that pretty soon here. But really to share with you, like, there's a lot of clubs on campus. You have a lot of choices of what to put your time towards, and like why SSS, besides the fact that I think it's pretty great. And primarily, I think it fills a gap in your education that you'll learn a lot in your classes. But definitely from my experience, what I learned in the club, I was able to take that and, you know, internship. Back in my senior year, I had tried and applied and got nowhere. But a friend of mine was working at Ames and said, I think you have a good skill set because we're in the club together. Can I give your contact info to my boss? And I said, yes, please. And, you know, when we had that interview, he looked at my resume pretty quickly, but what we talked about was, well, what did you do in the club? And what did I build? And what did I learn? And how did I overcome those challenges? And so I think that's primarily what you can really get out, is a hands-on engineering experience that gives you practical skills that you can take with you going into a job, going into grad school, you know, wherever you go next after UC Davis, as well as meeting some great people. Like, again, some of the best friends I have are either in the lab or in the club or both. And it just forms a support network, as, again, any upperclassman can definitely tell you how much working with these people really changes your education at Davis. So again, happy to be back in Davis, really happy to advise you guys. I'm here as a resource. Again, if you ever want to talk to anything about the club, about satellites, about grad school, again, I'm here as a resource. And I think really just seeing how the club has taken off since the, 4 years since I was here, and now you are this close to putting something in orbit. Like, again, it's just a dream come true, I'm sure, for myself, for everyone standing up here, and all of you sitting, is just like, this will actually happen. And it's because everyone works together and you have such great resources here. So again, really looking forward to what this school year holds, and welcome back to Davis.
Okay. Is it on? Yeah, it is. Okay, Sheree, if we can, yeah, let's get started. So I'll stand over here. Is it not responding? Well, it might be because of Zoom. I have Zoom running on my computer. So yeah, for those who don't know, Professor Robinson is our club advisor. So Professor Robinson is a former astronaut. He's made 4 trips to the International Space Station. And here he is repping the UC Davis flag. And as you can see on the bottom right, we're working to return back to the ISS with our current mission with the CubeSat. So next year. That is our goal. Next slide, Shri, please. Okay, and this is the agenda for today. So I'm going to be giving overview of the club so you can know what we do and what we offer. Then we're going to be talking about RealLock, mission RealLock. Give me once. Okay, yeah, so I'm going to be saying RealLock a lot, and it's okay if you don't know what RealLock is. We'll go more in depth. The leads will go more in depth on that later. And we're going to have each lead of mission RealLock present what their teams are about. Then we'll move on to RealLock 2. And then finally, we'll talk about the future of the club, and we'll have some alumni talk about their experience. Oh, and at the very end, we'll have each team at each corner, and you guys will have the opportunity to do a meet and greet with them to answer any questions you might have. So this is the administration team. I don't think I introduced myself. My name is Chris. Milena and I are the co-presidents. Shri right there is our secretary, and Ashe and Ray right there are our vice presidents. They're going to be taking over once Milena and I graduate this quarter. And like as I mentioned, Professor Robinson is our faculty advisor. Next slide, Shri. Thank you. Okay. So this sentence pretty much summarizes what the club is about. So our goal is to provide undergraduates with the opportunity to get hands-on experience with space technology. We've done this by participating in challenges related to Mars habitats, moon rovers, and many others. So currently, as I mentioned, as you guys might know, we're designing our very first low Earth orbit nano satellite. Thank you, Shri. Okay, and this is the timeline. It shows all of the important events that have happened with the club. We've bolded a few of them that we'll mention right now. So as you can see, SSS was formed in 2014. It started off with just 2 members, and they would go to Professor Robinson's office, and they talk about satellites and anything space related. And they coined the term sat chats. The year after, we competed in the CubeSat competition. And in 2017 is when we first submitted the RealLoft, the mission that we're working on, the proposal for that. That's actually the same year that we started getting a lot more members interested in the club. In 2019, we participated in the Big Idea Challenge, which is right here. You can see a cool render of it. It's a Mars habitat. And our team, shown right below it, got to fly out to Langley, I believe, Research Center in Virginia. And one of our members, Corey George, is actually right there. So yeah, right now we're working on the RealLock 2 proposal, and we'll talk about that after RealLock 1. But yeah, next year, like I said, we're planning to launch this satellite into low Earth orbit, or deploy it into low Earth orbit. But yeah, with that said, like I said, I've said RealLock a lot. So I think now is a great time for Milena to tell you guys what the mission is all about. So Milena, oh yeah, you got it.
Thank you. Hi, everyone. As Chris said, my name is Milena, and I am your co-president and the project manager for the RealLoft mission. Before I get into the mission itself, let me go over. Wow, I'm so sorry, guys. Why don't I explain to you what RealLoft stands for? RealLoft stands for Remote Experimentation and Analysis of Low Earth Orbit Phenomena. The satellite itself is known as Spaceblock. Now, before I go over the mission itself, let me go over why it's so important to us. RealLoft is pioneering Davis's involvement in the world of CubeSats. We are the first CubeSat team here at Davis, and we are also Davis's first undergraduate-led CubeSat program. And Spaceblock will be the first ever CubeSat to test the use of hard disk drives on an alternative as an alternative to reaction wheels. There's more of you guys here than I thought. Now, what will RealLock do? There we go. Because this is our first mission, RealLoft is a technology demonstration for the bus that we developed to use for future Earth science missions. We will also attempt to prove that HDDs can act as reaction wheels. We received our launch contract from the CubeSat Launch Initiative. We plan to hand over our CubeSat to our deployer Nanoracks in July 2022, and it will be launched to the ISS that October. From there, the astronauts will deploy the CubeSat from the ISS in a deployer like that. Mission RealLoft is divided into 4 subsystems: attitude determination and control systems, computer science, electrical, and structures. Here we have the leadership for the mission, going down from management to the leads to the sub-leads, who you will all meet in just a second. And now to hear from each subsystem leads. Let's start off with our ADCS leads, Natasha and Chris.
All right, hello everyone. My name is Natasha. I'm one of the ADCS co-leads.
And hi everyone, my name is Chris. I am also ADCS co-lead. And ADCS, as you can see on the screen, stands for Attitude, Determination, and Control Systems. What does that mean? So to the purpose of ADCS, it has 2 main goals for our RealLock mission. The first is attitude determination. So what that means is being able to determine the orientation of the CubeSat when it's in space, because the CubeSat doesn't know where it's pointing. You see here on Earth, we know the ground's ground, the trees over there, California Hall's right here, but we need to know where the CubeSat is. And we want to ultimately point to the Earth. So it's important we know where is the CubeSat pointing and how can we get it to point where we want.
All right, so our other goal for ADCS, as Chris mentioned, is getting our CubeSat to point where we want. So once we figure out our orientation, we need to figure out how much we need to spin the CubeSat in order to point towards Earth so we can take clear pictures. So we've got a couple of actuators to do that. We've got our magnetorquer coils, reaction wheels, and hard disk drives. So we'll be going over our teams for each of those.
So the first subsystem is the magnetorquer coils. So the purpose of the magnetorquer coils. So if you remember the GIF earlier of the CubeSat being launched from the ISS earlier, what that does is once the CubeSat is launched from the ISS, it will start to rotate and orbit in different fashion or in undesirable fashions. And we want to mitigate this, right? Because the purpose of the CubeSat is to point its camera towards the Earth. So the way the magnetorquer coils work is they have a bunch of coils rounded around it, which when you run a current through it generates a magnetic field. And as you guys know, the Earth is surrounded by a magnetic field. So we can use this magnetic field to slow down the orientation of the CubeSat so that the magnets that the air core or the magnetorquers create align themselves with the Earth. So that helps slow down the CubeSat, but that poses a problem, right? Because if you align a magnet like this, it's still allowed to rotate about one of its axes, which is where the manufactured reactions come.
All right, so once we've detumbled the CubeSat, there we go. Okay, cool. So anyway, once we've detumbled the CubeSat, we can still spin about that one axis. So that's where we use the manufactured reaction wheels. We still need to be able to point at the Earth so we can take pictures. So reaction wheels work by conservation of angular momentum. You can see the reaction wheels on the upper right there. And when we spin those in one direction, the rest of the satellite has to spin the other way, just so that we're conserving the overall momentum of the satellite. So we can spin those in one direction so that we can control the CubeSat in the other direction. And similarly, when we slow them down, we can stabilize the CubeSat. So that way we can take clear pictures that aren't too blurry from spinning. So the manufactured reaction wheels are a great tool for pointing and stabilization, but the caveat is they're really expensive and kind of hard to manufacture. So we're working on a tech demonstration of using hard disk drives as an alternative.
So hard disk drives, why are we using a piece of equipment you might find in your computers? Essentially, hard disk drives, as you know, as Natasha mentioned before, manufactured reaction wheels are built by universities who are developing CubeSats for the first time. However, since they are built by a university for the first time, they're more prone to failure. And the reason that universities don't invest in industry manufactured reaction wheels is because they're really expensive. And if you're a broke college student like me, you don't want expensive. So you'll build it yourself. And if hard disk drives work as a manufactured reaction wheel, one, it will provide universities who are interested in building CubeSats a low-cost substitute for reaction wheels, and will allow them to evidently build their own. So those are hard disk drives. So far, we've talked about the three actuators on the CubeSat, the magnetorquer coils, the manufactured reaction wheels, and the hard disk drives. So that's cool for being able to point the CubeSat in a desired fashion. However, like I mentioned before, we need to also know where the CubeSat is pointing. And luckily for us, one of those is the sun sensors.
All right, so in order to control our actuators, we need to know how much we need to spin them. So the attitude determination is really important for that, for figuring out our orientation. So one mechanism we use is the sun sensors. So we need two reference frames in order to figure out our orientation. And conveniently, one of those can be the sun. So you can see a sun sensor on the upper right. It's that little pyramid structure. And what we're doing is we're installing one of those on each side of space block. So we can use those to measure sunlight and figure out our orientation relative to the sun. So we can combine that orientation with some information from our software algorithms and use that to figure out our overall orientation relative to Earth. So we do have a software team dedicated to that.
So as we mentioned before, the software team kind of takes everything together. They use the actuators, the magnetorquers, the MRWs, and the hard disk drives. And with special software that we develop, they tell the CubeSat what to do. And they're responsible for knowing where the CubeSat is pointing and controlling the CubeSat so that it points its nice cameras down towards the Earth, which is really helpful. However, one thing is, how are we going to test our algorithms? How are we going to test that our reaction wheels are spinning at the correct RPMs? Or how do we know the magnetorquers are generating the correct magnetic field? Well, luckily, we have the testing team.
All right, so our final subsystem for ADCS is testing. So testing is kind of a hybrid of all of our other subsystems. They're responsible for developing test procedures and rigs so we can test out all of our other components. So for example, in the upper right, that's a fishing line test. So what we did is we attached a camera to the end of a fishing line and spun it around really fast. So using that, we could figure out how slow the CubeSat needs to be spinning so we can get clear pictures of the Earth. So that's just one example of a bunch of tests that we would do for all of our different components. So if all the subsystems sound interesting to you or you just can't pick a favorite, testing is a really good option because you get to work with all of them. So that's all of our subsystems. I'll be handing it off to Jackie to talk about our computer systems.
Thank you. Hey, thank you. Okay. Hello, everyone. Before I start, I just want to get an idea. How many people are interested in computer science or computer systems? Raise your hand. Okay. Yeah. Yay, that's a good amount. Okay. All right. So my name is Jackie. I'm the computer systems advisor for the club, and I will be going over what the computer systems is responsible for, what we've done so far, and what comes next. So going over the team overview, the computer systems is working on creating flight software for the RealLoft missions. Our software needs to manage orbital navigation and orientation, take data from our experiments, and communicate back the data to the ground station. Okay, so what Computer Systems has done so far, we've developed a concept of operations, which essentially lays out the requirements that we need as developers to produce our code. We've standardized the production of our code using GitHub and Agile methodology, and a joint effort between ADCS and Computer Systems. They've successfully ran the first test of the HDD reaction wheel. So going over Computer Systems' upcoming tasks, we need to develop a Linux kernel, which essentially is it's the core of the it's the core of the computer's operations. So we also need to pull together code from other teams such as ADCS and electrical using GitHub, and we need to test our code that we write using a flat sat. So a flat sat essentially is it's all of the electrical components of the satellite laid out flat, and it'll allow us to test our code once we develop it. So if you're interested in learning more about the specific roles and opportunities that are available, if you want to join Computer Systems, feel free to chat with me after this meeting. Thank you. Now I will hand it off to Brandon to talk about electrical.
Hello, my name is Brandon. I'm the lead of the electrical team. The main thing that our team does is the design, the assembly, and the testing of all the printed circuit boards or PCBs that are going to go into the satellite. You saw an example of that with that flat set picture that was in Jackie's presentation. But so what the electrical team works on, we actually work on every level of the PCB design process. So what that means is that we start with a basic circuit concept that we put on a breadboard. That'll look like a lot of things depending on what the specific function of the circuit is meant to be, which I'll go into later. But once we've actually nailed down a concept and we have a circuit that's working, we move on to the design phase. And so we use two different pieces of software to do this, KiCad and Altium Designer. And this lets us actually make a CAD model of what our PCB is physically going to look like. And we send this off to a manufacturer. They send us back a blank circuit board, and we do the assembly ourselves as well. During the pandemic, we were able to construct our own. Sorry, lost my train of thought there. We were able to construct our own reflow oven and a lot of other equipment that's actually necessary to assemble the PCB. So we're very self-sufficient in the sense that we have all of our own equipment to do the assembly ourselves for our PCBs. We order our parts, and we get a lot of hands-on experience that way. So the types of boards and the different functions that our circuit boards actually provide to the CubeSat are pretty broad. So we have power systems. So that includes our solar panels, our battery charging circuit, our power distribution systems, and that sort of thing. So we design all those, test all those. Our flight computer. So the flight computer on our satellite is actually a Raspberry Pi compute module. So we have a carrier board for that. That also has a few sensors and cameras, etc., like a GPS and all that. And so we design a PCB that has all those on them. Also the communications array. So we have everything that's going to be processing, sending information to and from the ground stations on Earth using our antennas. We do that as well. And some miscellaneous PCBs. So we work very closely with ADCS to develop some PCBs for them. So such as a magnetic coils control PCB for the coils that they were talking about earlier. We also design some PCBs associated with the sun sensors. So if you join electrical, there is a lot of opportunity to work on things that ADCS is working on. And in that vein, there's also a lot of opportunities to write some code as well, because in the process of our own testing, it becomes necessary a lot of the time to just write some code to test maybe a certain sensor to make sure you wire it up correctly, to make sure there's no issues with the integrity of your signals, that sort of thing. So there are opportunities to write code. And so another thing is that, particularly because we're in a critical ending phase of the mission, there's going to be a lot of opportunities to do some hands-on work. And I think Adam touched on it really well, is that there's a gap to be filled in the experience that you would get just from classes alone. And so our team's really going to try and emphasize hands-on experience. So there's a business incubator in Davis called Inventopia, and the owner and operator of it, Tim Keller, has been generous enough to provide the lab space and a lot of equipment to us to use. So he's allowed us to keep a lot of our equipment there. And so that's where we're going to be doing a lot of hands-on work. So assembly of the PCBs, like I said, testing of the PCBs, using things like oscilloscopes, logic analyzers, that sort of thing, to do the assembly and verification of all of our circuits. There's a lot of industry relevant experience that we get here. So I personally have an internship that's been running for about 2 years now that I was only able to get because of experience I got through this club. And I know there's at least a couple of the members who have internships right now. Our power systems lead, Abdallah, who couldn't be here today, has an internship with SunPower. And there are some alumni we have, the previous lead specifically working in NASA along with Adam. So if anybody has any questions, as Chris and Lena said, I'll be happy to answer them after the presentation. But for now, I'm going to hand it off to structures.
So we hold this one. And
Both of them basically, treat them both like mics.
okay. How's everyone doing? So raise your hand on space. Great, fantastic. The space is very dead, right? So what? Anyways, the space is obviously quite deadly. It's an extremely inhospitable environment that presents a whole slew of challenges with regards to the design of the CubeSat and RealLoft 1. So our subteam is essentially responsible for safeguarding and protecting our scientific instrumentation payload. As previous individuals have spoken about, our scientific payload needs to be capable of surviving the entire mission lifetime, all the way from launch and integration into the deployment into the space environment. And so even though our subteam is straightforward in theory, it's a deceptively simple challenge. And so the entire purpose of structures is characterizing all of the different facets of developing a robust and reliable CubeSat, and then splitting them into our different subteams within structures. And so a big part of this is essentially we're going through the entire mechanical product design life cycle, all the way from deriving our mission requirements into a design that is, again, robust and reliable, and then turning that into something that is manufacturable, and then finally something that can be assembled. Next slide, please. Okay. Right.
All right, so the first sub-team that I'm going to be talking about today is the mechanical design sub-team. So what we're trying to focus on with this sub-team is teaching and nurturing the tools that will be needed in the development of RealLoft 2. This will include like using SolidWorks, getting your hands dirty with some kind of CAD software. You might have done it in some of your classes, you might have not if you're freshmen, but you'll get more experience in developing something that might be actually like manufactured. We might have some experience of making a CubeSat that our manufacturer said, you might want to go back to the drawing board a little bit. But that's a lesson that we want to teach everyone here, or that does join structures. We also want to teach geometric dimensioning and tolerancing, also known as GD&T. This is the industry practice, and it's something that's implemented so that engineers are able to communicate with the machinists, and so that when you do go from computer to actual manufacturing, that the machinist is more able to realize your design. And also we would have workshops on these. So, you know, we do have like some hands-on learning and you guys will have some experience with it. And what those workshops will lead to is actually designing a chassis for RealLoft 2, or proposing different kinds of chassis and working in like a more of a competitive scene where you work on one iteration and continue on until someone actually has something that's viable. And with that development towards RealLoft 2, we want to iterate on RealLoft 1's current design and see what kind of improvements that can be made and developed, so that there is a more practical satellite for the use of RealLoft 3, and also the development of a deployable solar panel that will be needed for our 3U CubeSat mission. If you guys didn't know, our current CubeSat's a 2U, and then so the next CubeSat is going to be a 3U. I'm going to hand it back to Xiao for talking about manufacturing and assembly.
Right. So go back to the past slide. Yep, thank you. So essentially, over the summer, over the course of the pandemic, Structures has been working hard to foster a partnership with a local makerspace called Inventopia. Inventopia is essentially a place where they have a bunch of like CNC machines and lathes and all kinds of different devices that are going to help us realize the fabrication of RealLoft 1. So where we are essentially in the product life cycle is we have finished the mechanical design for RealLoft 1, and we're about to enter production for RealLoft 1. And so over the next month or so, roughly, based off the timeline, we're going to go to Inventopia and essentially learn how to create all the different components, as well as Stefan mentioned geometric dimensioning and tolerancing, manufacturing principles that can help make manufacturing easier. After that, becomes quite straightforward because we have all the different components laid out. There are various like testing stages that you have to go through, such as something called verification and validation, or V&V. Verification and validation is just checking all the components and making sure that they fit together correctly. And that directly feeds into assembly. So we're going to get in the scrubs, we're going to have a clean room, and we're going to actually put the pieces together. JPS. What else? Well, let me go ahead and hand it over. I'm going to talk about our analysis subteams. Next slide, please.
Thank you, Zhao, and thank you, Stefan, our current leads for structures. My name is Justin. I am the mechanical lead for the mechanical analysis subteams. Mechanical analysis answers a lot of the engineering problems with the CubeSat. We have three main problems we're trying to solve. First is the CubeSat inherent characteristics due to random vibration and acceleration loads. There's also a third component, the modal analysis. You may not know these terms now, but if you are diligent and looking to work into this team, we can offer a lot of the resources to help you understand. But modal analysis will also discover the mode shapes due to different frequencies. All these are important for our first stage of delivery, which is the space vehicle launch to low Earth orbit. So why should you choose a subteam? There are very much gray areas of analysis, but we will expose you to advanced industry analysis experience used by many companies. So far in the past year, we started through SolidWorks, moved to ANSYS, and now we're finalizing through Autodesk Inventor. Our solvers, Nastran, which is NASA structural analysis solver, will help verify that our analysis is correct, and we can hand it off to third-party companies. Many of these concepts, such as solid mechanics, fastener selection, and modal analysis, are covered in Aeromech junior and senior design classes. If you're interested to learn more, and I know many of you are freshmen, but eventually you will be exposed to this, and it's a great opportunity to be prepared when that time comes. Yeah, I'll pass, once we solve these issues during launch, the CubeSat will be ready in low Earth orbit, and I'll pass it on to our thermal lead, Angel.
Thank you very much, Justin. So when the CubeSat is in space, it would complete transient orbits, and it will undergo many different temperature adjustments, or there's going to be many extremes that we want to take into account for, so that everything in the CubeSat is still stays operational. And the way we do that is we try to make a simple model of the CubeSat using thermal desktop, which is an industry standard for thermal analysis. With this software, we are able to create the simulations that we need for the CubeSat, and then compare them with hand calculations that we would need to do ourselves. So if anyone is interested in getting into thermal analysis and making sure that things don't, burn up, this would be a great team to join. Ideally, you'd want to have some background with heat transfer and thermodynamics. But we try to teach you what we can, and especially thermal desktop, which is a very useful software for us. And with that, I'll hand it off to the RealLoft 2. Oh, sorry.
Good. Hi, I just wanted to introduce myself. I am one of the sub-leads for mechanical design that was already discussed. And in case you have any questions or just want to say hi, I'm happily willing to answer any questions after the presentation. And I'm going to hand it over to Shah.
Yeah, so again, structures is fairly straightforward, but quite multifaceted. We're essentially looking for individuals who have a genuine sense for creativity and in designing robust and reliable systems. We'll be in the corner, the far right of the room, and you'll be able to speak to all of us. What else? This is Stefan, by the way.
Oh,
yeah. Sorry, we didn't introduce ourselves earlier. This is Stefan. I'm Xiao. We're both infrastructure. So, without further ado, we'll just pass it off to Elena for RealLoft 2.
We noticed it's getting a little bit dark in here, so we're gonna try to change the light settings. So let's switch it up to lecture speaking. No, I think that is it. Let's do a pre-post lecture. Nothing's happening. Well, that's okay. We can deal with that. But yeah, next up, Shri, may you change the slide. Next up is RealLoft 2. So that was all RealLoft 1. We just finished talking about all these subsystems. Next is our vice presidents, Astra and Ray. They're going to talk about RealLoft 2 now. And here is the Zoom.
Hey everyone, I'm Ashay, Vice President along with Ray this year. And with RealLoft 1 nearing the completion, SSS is planning another ambitious mission, RealLoft 2. Similar to RealLoft 1, we would have to submit a proposal to NASA CSLI, and it has to be accepted in order to move forward with the mission. The main objective of the mission would be the technology demonstration with high emphasis on innovation. Oh, could you move the slide? Could you move the slide, please? In order to ensure the acceptance of our proposal, we would need a highly motivated research and development team. The main purpose of this team would be to utilize NASA strategic plan to come up with a space-breaking proposal for UC Davis's second but not the last CubeSat mission. Now Ray will talk to some little more about RealLoft 2. Thank you.
Thank you, Asha. I'm Ray, and I'm the second vice president of SSS. And continuing on with RealLoft 2, we are currently looking for 20 to 30 members to take part in research and development, or R&D for short. This team would be, this team's primary focus is to develop several mission proposals to send to NASA's CLSI division. And we get, let's say about like 6 or 8 proposals, we then host some internal competitions and end up choosing one of them to send. And each of the proposals would be guided by NASA's goals, which is to discover, explore, develop, and enable. And with RealLoft 1 mission slowly coming to an end, the R&D team is crucial in pushing the club forward, which would allow new and current members to pioneer innovation, as well as carry on the legacy of SSS once we're, once we all graduate and all that good stuff. And if you guys have any questions for RealLoft 2, we're gonna be in this corner over here. Yeah. And that's pretty much it for RealLoft 2.
Thank you. Yeah, I mean, so just to reiterate on that, you guys are the future of SSS. So I highly, highly recommend considering RealLock 2, because your choices are going to define the future projects of SSS. So, oh, that's perfect. So yeah, for the future of SSS, so pretty much our goal is greater than RealLock or RealLock 2. So we want to help UC Davis become the space hub of Northern California, much like how Cal Poly SLO is that of Central and Southern California. We want to help UC Davis become that. Secondly, we want to standardize our CubeSat bus. That includes everything, the structure, the electronics, and I think at the moment, most importantly, the software. And so yeah, just having a standard bus is going to help us push out CubeSats at a greater rate. And then lastly, we want to continue engineering these unique technologies. As our vice presidents just said, we want to keep creating these like novel solutions for these engineering problems, like the hard disk drive for ADCS. So yeah, this is the future of SSS, our goals. And I think this might be one of the last slides, yeah. So this slide is dedicated to the alumni. Our alumni have had the fortunate opportunity of getting these positions at these industry locations and schools. There's a lot more that just aren't on this list. These are the most recent ones. Oh, hello. These are the most recent ones. But with that said, I think, yeah, I mean, they're ready. I didn't even realize. So Corey, Abe, Kylie, Ricardo, and Thaddeus, they're going to share with you guys real quick their experiences, where they're at, and how SSS has helped them out. So I guess if you guys can just start off by your name and what you're feeling. We only have one working mic. Hey, I think we probably should. It's muted. Oh, yes. Here, I think, how about you go, and I'll give this to Kai or Corey.
Okay, here we go. Corey, this is yours. Hello.
This is mine?
Yeah, not to keep. Some of you may know us, some of you may not. My name is Abe. My name is Tyler. We'll present ourselves to you first. So we are actually one of the execs. We graduated from the Canadian department with both aerospace and mechanical degrees in 2020. Now we're master's students at UC Davis.
So we were execs for 2 years here, and we were members for 1 year before that. That meant that we had Chris and Natasha's positions right before them, and then we passed it along to them. Very proud of them. But we got to work with a whole bunch of things like magnet torquers, reaction wheels, the hard disk drives, and just everything.
Yeah, actually, thanks to SSS greatly. We were both of our internships that we earned for from NASA. Large part of it was due to SSS, and every interview I go to, I talk about SSS a lot, and I get a lot of questions about it too. I interned at Kennedy Space Center. Callie interned at Johnson Space Center. Corey interned at JPL. So and JSC. So yeah, and Stennis. The list goes on. So if you're really interested in aerospace, then SSS is really the place. But yeah, so Kylie and I, our master students, we're part of the HRVIP lab led by Professor Robinson, who some of you may be familiar with. And actually part of our master's thesis is, the core of our master's thesis is demonstrating the hard disk drives as reaction wheels. That's been discussed a bit, and we actually have part of our master's thesis in Kylie's hands right now. This is a Rock 1U CubeSat. It's fully functional. It has 3 hard drives in there, and it turns on and off and it spins. So if you want to check it out, it'll be over with the ADCS leads, Chris and Natasha, and we'd be very happy to talk to you more about ADCS, more about SSS, and engineering in general. So I'll pass it on to Corey next.
All right, cool. What's up, everybody? I didn't know I was going to say something until a few minutes ago, but I'm super overwhelmed right now by like how many people are in this room. Like, this is California Hall, and it's got to be like, I don't know, a third full, which is significant because like when I joined this club, like it was just a room full of people, and actually like, so when I first joined, we just got the idea to like, hey, let's make this we got this crazy idea. Let's propose to NASA, like, let's do an actual satellite. And literally everyone said, no, you can't do it. Our advisor said we couldn't do it. Like everyone was like, no, that's not a good idea. We're like, yeah, whatever. So we did it anyways. And we made this proposal, we submitted it, and they're like, yeah, we're gonna launch you. And we're like, holy shit. Like, that's crazy. Now we have to do it. And so so now like, but it's just like grown so much, and people have come through and like gone on to do just amazing things. Like, we have alum who are working at NASA. Like, I've worked at 3 centers. These guys have worked at different places. You know, Adam's worked at NASA, like, and not just NASA, but like Maxar and all these places. And like, honestly, it's just so cool. And it's a community. Like, all of us just like we're just friends, you know, and we're just like space nerds and just like doing cool stuff. So it's just so fun, and I know you're gonna love it and you're gonna get a lot out of it. So thank you so much for showing up today. Thank yourselves for showing up today. And yeah, that's all I had to say. Thanks. Oh. Yeah, no, she reminded me to say what I'm working on. So right now I'm a grad student here at UC Davis, and I'm working on the next generation of deep space habitat. So we're trying to figure out, what kind of technology do you need to develop a habitat that's going to be in orbit or on Mars? So I'm working on basically, how does this habitat think about itself? You know, how does it keep track of its own states, its own degradation, and keep track of itself? So it's pretty cool. It's a lot of fun. And if you have any more questions, you can hit me up. I'll be around.
All right, thank you, Corey. Wow, that was a lot harder than me to be. But hello, everyone. My name is Ricardo. I'm a first-year master's student here at Davis now. So I just graduated last year from here at UC Davis as well, and of course SSS. If you were involved with the club last year, then maybe you remember me as the systems engineer last year, and the year before that, I was the structures lead. And so that's kind of what I've been up to with this club and where I'm at now. But 3 years ago, if we go back in time, 3 years ago, 2018, I was just a nervous sophomore engineering student. And I kind of honestly didn't really know what aerospace engineering was, or how, like, if you get a job, what you really do. And so I was, really scared, thinking of actually not doing engineering at that point anymore. But then I found this club, and this club is really the bridge between where I was 3 years ago and where I'm at now. And I'm definitely like happy to be where I'm at right now. And so this club really helped me develop in many ways, academically, professionally, and probably most importantly, personally. Academically, my interest in the subject area just exploded, and my motivation to like work hard in classes and get good grades and want to continue to grad school just really increased. And so in that regard, it helped me out a lot. Professionally, this club exposed us to, research conferences and other events to practice networking and make connections with people in the industry. And of course, the connections with the alumni before me and before us was pretty cool as well. And then lastly, personally, I think most of us can say we found probably our core friend group through this club. I can definitely say I probably found some lifelong friends. So hopefully with you being here today, and if you make the decision to join this club, hopefully all of that can happen for you as well. But it all starts with, of course, you making that choice and putting yourself out there, and kind of what you put in is what you get out. So I wish all of that for all of you here today. And so now I'm gonna pass it on to our last alumni here, Donnie.
That's going to be hard to follow up. So hello, everyone. My name is Thaddeus Slim. I am also a first-year grad student. I did my mechanical engineering here at Davis, and I was part of SSS. I'm now part of the MAE department, hopefully getting my master's someday. Unlike everyone else here, I didn't have a fancy role. I was just a structures person under that department, and it was fun. I enjoyed it. There are things in SSS you learn, you do, you work with. That's what I've noticed is what engineers use. So I'm the only person I think who has done an internship not in the aerospace industry. I work for Zeiss. We make optometry equipment, but even there we talk about GD&T, like how do I do geometric dimensioning and tolerancing, and why is it so important? Why do none of my 3D prints work? Please, someone help me. But those are the kinds of things that you're gonna learn if you join structures, and I'm sure the other teams are useful too. So I forgot that there's ADCS up here with me. But I've been told by engineers, hey, students don't really work on long projects. You go work for a quarter, maybe on one project, maybe senior design over 2 quarters, but you hardly get to work on something that lasts a long time. And it's iterative. It's gone through several generations. It's gone through several years of work from many, many different people. And you get to work with that. You get to learn, you get to work together, you get to work in a team, something that's also rare for your undergraduate experience. To elaborate on what Ricardo said, I made some of my closest friends at Davis here, and undergraduate is hard. I'm not a genius. I'm not a smart person, unlike everyone here, probably. I got in by luck. So, but it gave me a support group. It gave me a community to get through my bachelor's, to get my degree, to just have friends to spend time with. Undergraduate is hard, in my opinion. And I greatly appreciated my time here. What I learned here and the friends that I made, it's made the experience so much better, so much easier, aside from all the cool things I've got to do. I mean, we're getting a satellite in space, for goodness sake. I want that. That's cool. So thank you so much for all being here.
All right. Yeah. Thank you, guys. Okay. Well, that was our alumni. And now we have a special guest. I'm not sure if you guys saw them come in, but Professor Robinson is right here. So would you, would you like to join us, Professor Robinson? There's 2 mics. This one's on Zoom, so there's 2 mics.
Okay.
Yeah, there we go.
Hi, everybody. Wow, there's a lot of you. How many of you want to go to space yourself? How many of you want to work in the space industry? I suppose that's why you're here, right? All right. There's a lot of other reasons for being here, and I hope to hear about all of them sometime during this year. So I'm Professor Robinson, the faculty advisor, which means I mostly learn from you. I don't provide tons of guidance or advice. You know, this is your club. I hope I can help out now and again as things get, you know, when you deal with things like the bureaucracy of NASA and how to figure all that out. It's, you know, it's getting close. We're going to launch a UC Davis satellite. That is the most awesome thing. Not all that many things from UC Davis have gotten into space. But I went to UC Davis. So I guess I've been a satellite. Yeah, I did my undergrad here. Got the double major of mechanical and aerospace engineering. It wasn't my only major. I actually changed majors to double majored in art and pre-med. Bad idea. The art was easy, the pre-med, so I came back to engineering and I was glad I did. And then I did lots of stuff and I came back to UC Davis after doing lots of stuff about 9 years ago. And this club, as you heard about in the history section here, started not too long after that. So it's just wonderful to see what's happened and the kind of leadership we have this year and all the leadership we've had all along. So thanks for being here. It's going to be a wonderful year and I can't wait to see what happens. Oh yeah. All right.
Smile, smile.
This is history. You over there. Thank you.
All right. Okay, now it's almost time to go to our corners. But before you do that, we just want you guys to join our Discord server real quick. You can bring out your phone, open up the camera app, and just hover over that and click the link that is following. If you don't have Discord, feel free to download that right now, and the leads will provide this QR code later if you don't have it right now. I'll give you like a few seconds. Once you're in our Discord server, just go to roles and click on the icons. They correspond to the sub-team that you are interested in. You can click on more than one. But yeah, we just want to have that done now because it's usually a little complicated if we wait. Give you guys 10 seconds. Oh, I should have mentioned, when you click on the icons, you're going to get access to all of the channels for each subsystem where you can find a whole bunch of information regarding that team. But I think we can. Good? Okay, yeah, we can just move on and then you guys can continue doing that at the corner. So Sri, if you can go to the next slide. Like I said, the leads are going to have that QR code so you can scan it anywhere. So this is our setup. So front podium is where I'm at. So RealLoft 2 is going to be right here, the research and development team. Then you're going to have computer systems in that corner. In my far right back, we're going to have ADCS. Then we're going to have electrical on to my left and structures to my far left. I know you guys have a lot of questions, so feel free to ask them there. If you have any admin questions, we'll be up here. Thank you.